We're going to now talk about exponential functions. Now you see in this word, exponential functions, you see the word exponent. That's something that we have used and talked about before. For example, here are some x to the third, or x cubed, which once again, as a quick reminder, x is the base, 3 is the exponent, and mathematically this means you take the base times itself 3 times. Five to the fourth means you take 5 times itself 4 times. Now if we want to write this out as a number, 25, I think it's probably 625. Now we also ended up we looked at negative exponents. Hopefully you remember what the rule is about negative exponents. Normally we like to make a negative exponent positive, and we can do that if we flip it. In other words, 5 to the negative 2 equals 1 over 5 squared. And if you ever have a case where if you had something like this, where your negative exponents start in the bottom, if you want to make the exponents positive, they flip. In this case, they go to the top. And we would probably write this as 8x squared. So exponents can be whole numbers, they can be negative numbers, integers also. Sometimes the exponent is 0. What's the special rule about having an exponent of 0? It always equals 1. So even if we took a variable, a to the 0 equals 1. Now the last thing, as sort of a quick review, so we have basically like integers, right? Positive numbers, negative numbers, even 0. Another thing we did we looked at exponents when they were fractions. And we learned that we call these rational exponents. And we learned you can always convert a rational exponent into like in this case, a square root. So your denominator becomes your root. The base goes in here, the numerator. Now normally, of course, when the root or the index is 2, you don't put it there. When there's nothing there, we know it's a square root. Now a quick review, because I think there may be a homework problem like this. If they ask you to simplify this, 8 to the 2/3. Here's how we learned to do it. My root or index is 3. Now my numerator squared, I could put the square in here, which is perfectly fine, but I have an alternate. And the other way makes this problem a little easier to solve, where you can put the square way outside. Because then the cube root of 8, which means what number times itself, 3 times equals 8, is 2. And then you still have the square, the 2 squared is 4. All right, so that's a quick review of what we have done so far with exponents. Now I want you to notice something about all the examples I've done. Let's look at all the actual exponents. 3, 4, -2, down here -3, -2, 0, 0, 1/2, 2/3. So far, all the exponents have been numbers. But what would happen, instead of having the exponent be numbers, how about all of a sudden you stick a variable into the exponent, or it's a part of the exponent. When you have variables up in the exponent, those are called exponential functions. So, let me quickly go back here to one more thing. Because once again, I think you may have some problems homework like this. What happens you may occasionally have to calculate something like 5 to the 1.7th. There's no way to simplify it. There's no way to do it in our head. And I'm telling you now, for the rest of class, you're going to have to be able to use your calculator a lot and understand how to use it. Now, everybody's calculators are different. So what I'm going to show you in a minute is how to use mine, but yours may be different. So everybody's going to have to learn how to use your own calculators. Because this kind of problem, the only way I'm going to figure out what number this equals is to use a calculator. Now in my calculator, now yours may be different, I have a key. The little key is y to the x. So that's a key that helps me calculate these exponents. And for my calculator, what you do is I'm going to enter the 5, and then I hit the y to the x key, and then I enter the exponent, and it equals, and it gives you the number. So see if you can see it here. Here's this y to the x key. So 5 to the 1/7. Enter 5. Whoops, I got to turn it on first. By the way, this is just an old Texas instrument. This is probably about 15, 20 years old, but perfectly fine for what we need. So anyway, 5 to the 1/7, 5. Then I hit my y to the x key. Then I enter my exponent, 1.7, and it equals, and there it is. Of course, it's a big long number. Maybe I'll round it off to maybe 2 decimal places. So 15.43. So that's just a heads up when we're talking about exponents. Because we can also have decimals like this, which we can't do a whole lot with, but we can go and grab our calculators and actually calculate this. All right. Sorry, now jumping back. So now what happens when we start having variables in the exponent? We call these exponential functions. Now what I want to do first is see what these exponential functions look like. And actually, I'm going to graph two exponential functions. The first one I'm going to graph is y equals 2 to the x. And you're going to see in a minute, the way I'm going to graph this is I'm going to create a data table, an xy data table, figure out some values, then graph those points. And then actually on the same graph, almost looks the same, except up here the base is 2, down here the base is 1/2. So I'm going to graph both of these on the same graph and see how they look. Now before I do it, I want to give you a little heads up, and I'll explain it in a few minutes, but let me give you a little sneak preview, and then when we talk about it, you'll remember I said it. When you have exponential functions, I'm telling you right now. Oh, sorry. A base of 1 is like a dividing line. You have no idea what that probably means, but you will in a few minutes. So for this first one, what's my base? My base is 2. And the second one, my base is 1/2. Now with exponential functions, we're going to look at when the base is a positive number. The exponent can be positive or negative. You'll see in a few minutes, but we're only going to look at functions where the base is positive. So now I'm going to go, I brought in, so like a piece of graph paper. I'm going to quickly figure out some points for each of these graphs and then try and graph them, and then we'll see how they compare. So here we go. Let me go off to the side. So here's the first equation, y equals 2 to the x. And a lot of times when you have an equation and you want to create a graph, you simply create your xy data table. And I'm going to, for now, I'll let x equals 0, and then 1, and then 2, and -1, -2. So when x is 0, what's y going to be? Well, 2 to the 0 is 1. When x is 1, 2 to the first is 2. When x is 2, 2 squared is 4. Now some are interesting. When x is -1, 2 to the -1, if I want to make that a positive exponent, it becomes 1/2, right? And 2 to the -2 becomes 1/2 squared, which is 1/4. Now let me graph these 5 points, and then we'll see if that's enough points to sort of see what this graph might look like. So x is 0, y is 1. X is 1, y is 2. X is 2, y is 4. Now when x is -1, y is 1/2. When x is -2, y is 1/4. Maybe we'll do 2 more points. How about when x is 3 and -3? When x is 3, that's 8. And when x is -3, that's 1/8. If I try and connect these, let's see if I can sort of draw it here. That's what the graph looks like. And we call this, whenever you have this kind of graph or this kind of equation, we call it exponential growth. And that's probably a word you've heard used before. When you're told something's growing exponentially, you know what that means? It's growing really fast, really quick. And that's what happens. For instance, just for fun, if I put in 10 for x, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I go here to 10 and put it in and then try and graph my point, if I grab my calculator, 2 to the 10th, so 2y to the x 10 is 1,024. That means I'd have to count over 1,000 little squares. X is 10 right here, and I have to go up to over 2,000, which means this thing has gotten really high up, really fast. That's called exponential growth. Now let's look at the second graph I said. Instead of y to the 2x, let's look at y to the 1/2 x. And what I want you to realize as I'm working this is the base here for this one, my first one, the base is 2, which is larger than 1. Here, my base is going to be 1/2, which is actually less than 1. Let's go ahead and create our data table. It's important to see what this graph looks like and then compare the two graphs. So once again, we'll go 0, 1, 2, -1, -2. This one's a little trickier. So when x is 0, 1/2 to the 0 is still just 1. When x is 1, 1/2 to the first, so it's 1/2. When x is 2, it's 1/2 squared, which ends up being 1/4. Now what happens when x is -1? Let's talk about that. If you remember, when you have a fraction and it's raised to a negative exponent, the flipping, in effect, causes you to just flip this fraction and make the exponent positive. Which is basically just 2. 1/2 to the -2, if you do the math, ends up being 4. So let's go graph these points on the same graph and see what it looks like. So 0, 1, it's interesting, both graphs have that point in common. 1, 1/2. So here's x1, y 1/2. 2, 1/4. -1, 2. -1's 2. And then -2 is 4. And I think if I did -3, it would be 8. You notice this graph it's almost like the mirror image of this one. So this is the graph of y equals 1/2 x. Now you notice, so as x gets larger and positive, the y to the 2x, we say explodes. It gets really big, exponential growth. But as x gets large, what happens to y to 1/2 to the x? It starts to decrease and gets smaller and smaller and gets very, very close to 0. That's why we call this exponential decay. Decay means it drops or goes down. Now the key is, obviously, what the base. And I said The whole key is what's the base, and the base of 1 is the dividing line. So here, here's like my possible bases. If the base is between 0 and 1, a graph will always look like this. If the base is ever larger than 1, then we say it's a growth curve. So we're going to have problems later on. We're going to have story problems where they give us, I think later on, if I look at my notes, let me just throw this up there just to sort of prove to you. We have some, this is going to be a problem where we look at elk out in nature. And there's an equation where we have 0.9 raised to the t power. T is time. So t is just a number that's increasing. If I had this kind of a expression in my function, what kind of graph would I have? What kind of function would I have? Well, the key is, look at my base. Since the base is less than 1, this is going to be a decaying graph. If the next problem, I had my equation was like 2.3t, and I went to graph it. This is going to be a growth curve. And the key is, what's the base? If the base is between 0 and 1, it's going to be a decay. If the base is greater than 1, it's growth, exponential growth. All right, that becomes important, especially with story problems and also some graphing problems. So, now, let's go ahead, before we stop this video, go to the next one. Let's look at now one of the key things we're going to do. Solving exponential equations. Although, I just remembered there's one more thing I need to talk about. So actually, I think what I'll probably do is talk about this last point and then stop. And then the next video will cover solving exponential equations. So here's something that we have to cover. So let's look at some examples. I'll even write it in function notation just for fun. Some exponential functions. 2 to the x. You can have things like this, where your exponent is this expression 2x minus 1. You know, as long as you have an x somewhere in the exponent, it is a exponential function. Now, what if I had this? And at first, this won't make sense, but let me write it and explain. What if I write another exponential function, and here's my base, 2.71828 raised to the x power. And you might think, why would you choose just some kind of random decimal number as your base? Seems sort of crazy. And I agree. If it was just some kind of random decimal number, it would sort of be crazy to try and include it when we're teaching exponential functions. But the interesting thing is, it's actually not just a random decimal number. This is a special number in nature that God made. At least that's what I believe. God sort of made it. It occurs naturally in nature. You're going to see later on, we're going to do some story problems where we're going to use this number. It's almost like, you know, do you remember when you were learning about geometry and circles? And they said, what's the area of a circle? If you remember, pi r squared. And someone might say, what is this pi? I said, oh, that's just that special number, 3.1415, goes on forever. Pi is a special number that occurs in nature. Once again, it's like a number God made. Well, there's a second number. Pi is 3.1415, and it goes on forever. This number is 2.71828. And just like 3.1415 has a special name, we call it pi. This has a special name, and the people in the math world just give it the symbol E. So this really becomes e to the x. Matter of fact, because this happens so often and is used so much, they have to give it a name. These we would call exponential functions, but when the base is e, they call this the natural. Can I spell? Natural exponential function. The difference is the word natural. When you have the word natural here, that means the base is going to be e. So I know sometimes it can be very confusing, because all of a sudden you see this e, and sometimes you want to think it's a variable, but whenever you see the letter e, do not think of it as a variable. Matter of fact, if say you were given a problem like this, and you were asked what does that equal, you might think, oh, is e like a variable, or how am I supposed to do this? No, e's not a variable. If you really get stuck and are confused for a while, you can even do this. Every time you see an e, you can say, well, e just means 2.71828. And then you do that calculation. But of course, you don't want to keep doing this. I'm just saying initially, when you're learning this stuff, if it helps you, always think to yourself that e is just a number. As a matter of fact, the natural exponential function is important enough. You know what? If I go to my calculator, I don't know if you can see it. I have a little key. It's one of these yellow keys up above. So here's my y to the x key when I'm trying to calculate an exponential function. But look up here. Here this says e to the x. Of course, this calculator, if I want to execute this e to the x, I hit the yellow second key, and then I hit this button. It's important enough that they actually put it on my calculator. So really, if I was asked to do this problem right here, what is 2 times e to the 4th? What I do is turn on my calculator. In this case, the way we do this is we enter the exponent 4, and then you go execute the e to the x key. So for me, I have to hit the little second button, and then e to the x. That right there, 54.598, that is e to the 4th. And then for this problem, I multiply it by 2, and I'm all done. 109.20. All right, so we're talking about exponential functions. and we have this very special base, we're going to have problems where the base is going to be e. But remember, e is not a variable. E is actually a number. And just so you know, for those of you who are interested, the way they came up with e is this little formula equation, 1 plus 1 over n to the n, where n is just like you count. Once again, I just throw this out there. If you don't quite understand what's going on here, don't worry about it. The key is just to know e is this number, and actually this number goes on, but I just cut it off this far. But you don't even have to know this number, because whenever you need to use e, you can always just go and use your calculator. So in the next section, we're going to be solving problems like this. E to the x equals e to the 4. All right. Along with problems like this, notice here, what are my bases? 2 and 4 numbers. What's my base here? E. Although e is a number, it's just a special number. All right, so let me stop now. So that's some of the introduction, some of the definition, some of the background of exponential and natural exponential functions. The thing we're going to do is start working with exponential functions. The first thing we're going to do is try to solve some equations where we have an exponential function. So let me stop now and we'll start trying to figure out how do we solve these equations.